thank you for the presentation, and thank you to the organizers for giving me the opportunity to present part of my work. My co-authors, Aris Daniilidis, is also from the Technical University of Vienna, and Maribel Garrido and Jesus Jaramillo are from the Complutense University of Madrid. So today we'll be talking about horofunctions. I think we need to define them first, but a little bit of motivation. So let's recall what is a compactification. Pretty sure that the whole room knows better than me this part. Let X tau be a Hausdorff topological space. We say that a compact space Y sigma is a compactification if there is an homeomorphism from X to Y such that the image is dense. By here, homeomorphism, I mean be continuous onto its image. Some classical compactifications. If X is locally compact, then the one-point compactification or Alexandrov compactification. And if X tau is completely regular, the stone-check compactification. Also, in R, we have an extra one, which is plugging the mass plus infinity and minus infinity. So let's recall how one way to construct the stone-check compactification, which is we take a point on our topological space, and we see this point as an evaluation map onto the space of bounded continuous functions defined on X. For sure, here we have a product of compact spaces, so it's compact for the product topology. And one way to define it is just to say, let's take the closure of the image of this mapping. As I said before, each X can be seen as an evaluation map on the space of bounded continuous functions, but also we can see that we can see each function as a coordinate for this space. And so somehow we are using the space of continuous functions as a pivot space to construct a compactification. Here, we may change the space of functions, and therefore our coordinates will be more or lower, less, depending on what we decide. And since we are talking with metric spaces, the functions that we will choose are just the distance functions. So this was proposed by Gromov while he was studying something in hyperbolic geometry. And each X was sent to the evaluation map of the distance functions to a given point. And then he considered in the continuous functions the compact open topology, because this one, if the space is not bounded, we cannot put here the infinite norm, for instance. And he quotiented, take a quotient with the constant functions. Then he said that the horofunction extension of a metric space XD is just the closure of this I hat mapping into the space of continuous functions quotiented with the constant functions. As a remark, Y is continuous and injective. Another point of view that maybe it's better, at least for me, better to understand. Since we are using just the distance, we can consider the space of Lipschitz functions. And we say that lip B will be the real value 1 Lipschitz functions vanishing at B, where B is a fixed base point. And we can see that lip B is actually contained in this, again, compact product space and is closed for the product topology. And we define the same. Somehow, now we will decide that the quotient by constant is setting all the distance functions to be 0 at this base point. What we have? H is continuous and injective. The horofunction extension actually is homeomorphic to the closure of Hx. With this, due to the extension of Lipschitz functions, we can see easily that X is the horofunction extension of a metric space coincides with the one of its completion, and also that is a compact space. So we have a way to construct a compact space and a function that sends our initial space into the compact, which is injective and continuous. In the first slice, we introduce compactifications, and we ask for them to be continuous onto its image. This is our main question, when this map H is actually continuous. Okay, before that, some related works and applications. Actually, there has been a big literature about understanding which are the new functions that we can create with this Horofunction extension. This mainly from hyperbolic geometry. However, there has been also works from in the Banach space setting, trying to understand what is the new function that appears when our space is finite dimensional, or when our space is little p or capital LP. This was done by Walsh in the 27 or 28, and by Armando Gutierrez in his PhD thesis in Finland. Also, this metric compactification was applied for understanding better the dynamics of non-expansive operators, and also for fixed point theory of non-expansive operators recently, last year. And it has many other applications that there is a lot of literature to the respect. Okay. Oh yes. So now we go back to our main question. Is for which metric spaces we have that this map H is actually an homomorphism. Known examples. It's finite dimensional spaces, and when we try to compute the Euclidean space, we can get that this is homomorphic always to the closed unit ball. And whenever we take a point which is not zero and we send it like to the infinity with a ray, what we get is actually the minus the unitary vector corresponding to x. And so we can define what is called the Horofunction boundary, which are all the functions that we create which are not the distance given by our map H, and here are just the linear maps. For Hilbert spaces, it's known that this H is bicontinuous, and also if we take the unit sphere of the Hilbert space. Okay, a bit more general, the 2021, if X is proper metric space such that every ball is path connected, then H is an homomorphism. Here, this covers every Rn with any norm, and also every manifold, finite dimensional manifold. It doesn't cover the second one, for sure, because it's not proper. Proper means all the balls are compact. Okay. Yeah. Here, I want to say that the Horofunction extension is sensitive to the distance, or to the norm in our case. So this doesn't imply actually that the Euclidean space is the Horofunction extension is a compactification, does not immediately imply that it will be also a compactification for any finite dimensional normed space. Okay. But it's not always bicontinuous. Otherwise, we will not be having this talk today. Take X, the unit basis of little 1 and 0, and the base point 0. We can compute it. It's not difficult. And to show that H of En goes pointwise to H0. So it cannot be continuous because En is not converging to 0. And a similar proof actually shows that if we take the full space little 1, then H is not bicontinuous as well. So our main question, can we characterize those metric spaces such that H is bicontinuous or a homomorphism? Or equivalently, whether the Horofunction extension of a metric space is a compactification of our initial space? The answer is gladly yes. And we have it somehow. The Horofunction extension is a compactification if and only if I try to write it in the best way possible. Like for every there exists, for every there exists inequality. I said, okay, this doesn't look so nice. Let's try to put the quantifiers. It doesn't look nice either. Well, but we need a certain property for every point and every tolerance and a certain small set that will be compact set that satisfies something, and let us see just the inequality, which is somehow like W and Z should not be orthogonal in the L1 sense with respect to X. So this guy here cannot be the sum of these two numbers. It has applications, actually. If we take now any norm space and we take the unit sphere, actually we can prove that this space is, our function extension is a compactification. We fix our point X, we fix R, we set eta R equal to R, and the compact set, just the antipodal. We compute, and it holds true. So for our previous example of the sphere of the Hilbert space, actually it's true for any norm space. Okay, again, this sentence looks really not so clear for me. However, in a Banach space, whatever that happens in every point should happen in one point because it's quite homogeneous. And we can rewrite everything for Banach spaces. So let X be a norm space. Its or a function extension is a compactification if and only if there is a finite dimensional subspace such that the Hausdorff distance of the sphere of this finite dimensional space towards the full sphere is strictly lower than 2. Which canonical space does not satisfy this? Literal 1, right? Because En and Em, they are distant 2 always, and we can send one of the indices to the infinity. We were quite happy with this characterization, and we start producing several examples of whether this is true, when this is happening. Till we realize that this already exists in the literature, in a paper that was already mentioned today. Actually, it's equivalent to say that X is not an octahedral space. And so, okay, we have the equivalence, and now we can provide examples really easily, and we can use the whole literature that exists in octahedral spaces. So, for instance, the paper of Godefroy says that X admits an equivalent norm octahedral if and only if it contains literal 1 as a subspace. By the way, just for completeness, this result was extended to a literal 1 of kappa by Abraham, Antonio, and Gonzalo Martinez, who are here in the audience. And for instance, H is bicontinuous if X does not contain literal 1. For sure, if it doesn't contain literal 1, it cannot have an octahedral norm. Reflexive spaces, aspirant spaces, whatsoever. If X is the p-sum of 2 norm spaces, if X is the infinite sum of 2 norm spaces and one of them is finite dimensional. Okay. So far, so on. Okay, so, good. Okay. And there are more things that when I said that the Horofunction extension is sensitive to the distance or sensitive to the norm, here becomes clear. Because actually we prove that every norm space admits an equivalent norm such that its Horofunction extension is a compactification. How to do it? Well, it should be, if it's finite dimensional, it's clear because it was known even before our work. But now, if it's infinite dimensional, we can always decompose a space by Y direct sum with a line. And we consider the equivalent norm. Okay, let's do this two sum of the two spaces. Other set of examples. Since we are working with metric spaces, free Lipschitz spaces and Wasserstein spaces are classical in the literature. Here, I should also mention that Prochaska and Abraham Rueda, they did a full characterization of octaedrality in Lipschitz free spaces. Okay, and we have the following. If the free Lipschitz, if the Horofunction extension of the free Lipschitz is a compactification of it, or if the Wasserstein one space is a compactification, the Horofunction extension of the Wasserstein one space is a compactification of the space, then we have the same property for the underlying metric space. Just to mention, this one Wasserstein space is the space of probabilities with finite first moment. Okay. So that's all what I wanted to say. These are the main reference of our work. Gilles Godefroy in his seminal paper in octaedrality, then Gromov, this proceedings in Princeton, in which he defined his metric compactification, and the thesis and the several papers of Gutierrez, while he was trying to understand more precisely concrete examples on our faculty extensions for Banach spaces. Thank you for your attention.